Let's see how to do the spiral level ordered traversal of a binary tree. To do a spiral level ordered traversal, we start at the first level of the tree and we visit all the nodes left to right. Then we move to the second level and we visit all the nodes right to left. Then we move to the third level and we visit all the nodes left to right. Then we move to the fourth level, we visit them right to left, and so on all the way up until the last level. Let's see this with an example. So here we have a simple binary tree, and we begin with the first level and we visit all the nodes left to right. So in this case there is only one node, so we visit 1. Then we move to the next level and we visit them right to left, so it will be 3, 2. Then we move to the next level and we visit them left to right, so 4, 5, 6. Then the next level right to left, so 9, 8, 7. So the final output should be 1, 3, 2, 4, 5, 6, 9, 8, 7. To do this, we will be using two stacks. We begin by pushing the root of the tree to the first stack. So the root of the tree is 1, push it to stack 1. Then we go to stack 1 and we set the current node to the top of stack 1, so 1. We pop stack 1, we print the current node, and then we add the left child to stack 2, so 2. Then we add the right child to stack 2, so 3. Then we go back to stack 1. This time stack 1 is empty. This indicates that we're done processing the current level. So now we need to go process the next level. So we need to move to stack 2. Now with stack 2, we set the current node to the top of stack 2. So 3. We pop stack 2 and we print 3. Then we add first the right child and then the left child to stack 1. So the right child is 6. We push it to stack 1, and then 3 doesn't have a left child. So we're done with 3. Then we go back to stack 2 and we set current node to the top of stack 2, so it's 2. We pop stack 2, we print the current node, so 2, and then we add the right child to stack 1, so 5, and then we add the left child, so 4. Then we go back to stack 2 and we notice that stack 2 is empty, which means again that we're done processing this level, so we need to go now to stack 1 to process the next level. So we go back to stack 1 and we set the current node to the top of stack 1, so 4. We pop stack 1 and we print the current node. Then 4 doesn't have any children, so we're done with the 4. We go back to stack 1 and we set the current node to the top of stack 1, so 5. We pop stack 1 and we visit current node, so 5. Then we add the left child to stack 2, so 7. Then we add the right child to stack 2, 8. Then we're done with the 5. We go back to stack 1. We set current node to the top of stack 1, so 6. And we pop stack 1. We print the current node. And then we add the left child to stack 2, so 9. And then the right child, but 6 doesn't have a right child. We go back to stack 1. This time stack 1 is empty, which means we need to move to the next stack. So we set the current node to the top of stack 2, 9. We pop stack 2 and we print the current node. Then 9 doesn't have any children, so we're done with the 9. We go back to stack 2 and we set current to the top of stack 2, so 8. We pop stack 2, we print the current node, and we process the children of 8, but 8 doesn't have any children. So we're done with the 8. We go back to stack 2. We set the current node to the top of stack 2, so 7. We pop stack 2 and we visit the current node, so 7, and then 7 doesn't have any children. So we go back to stack 2. Stack 2 is empty, which means we're done with this level, and now we would move to stack 1 to process the next level. But stack 1 is empty. This indicates that there is no next level, and so we're done. So the final output would be 1, 3, 2, 4, 5, 6, 9, 8, 7, which indeed is the spiral level order traversal of this tree. Let's see how to implement this. So we'll have a function called spiral level order, which takes address to the root node and returns nothing. So the first thing we do, we check if root is null, because if root is null, the tree is empty, and so there is nothing to traverse. But if root is not null, we initialize our 2 stacks. And then we push the root node to the first stack. Then, what we're going to do, we're going to enter a loop from which we will exit within the body of the loop. And now, what we're going to do, we're going to process first stack 1. So while stack 1 is not empty, what we do, we set the current node to the top of stack 1. We pop stack 1. Then we print the current node. Then we check, does it have a left child? And if so, we push it to stack 2. So if current left is different from null, we push current left to stack 2. So stack 2, push current left. And then we check if current has a right child. So current right is different from null, in which case we also push it to stack 2. So stack 2, push current right. Then once we're done with stack 1, so once stack 1 becomes empty, what we do, we check if stack 2 is also empty. This means that there is no next level to process, which means that we're done. So if stack 2 is empty, we break out of the loop. But if it is not empty, this means that we need to process the next level. So we go through all the nodes in stack 2. So we do a similar thing. So while stack 2 is not empty, we set the current node to the top of stack 2. We pop stack 2, and then we print the current node. And now we first check if current has a right child, in which case we add it to stack 1. And only then we will check the left child. So if current right is different from null, we push to stack 1, current right. Then current left is different from null. We push it to stack 1. Now, once we're done with stack 2, what we do again, we check if stack 1 is empty. This means that there is no next level to process. And so we can break out of the loop. And that's the entire function. Let's verify that it actually works by running through an example. So here we have the same binary tree we've seen before with root 1. So we call spiral level order passing root 1. So root is not null. We initialize the 2 stacks st1 and st2. We push to stack 1 root, so 1, and we enter this loop, and we see Well, stack 1 is not empty, stack 1 is not empty. We set current to the top of stack 1, so 1. We pop stack 1, then we print current, and we check, is current left different from null? The left of 1 is 2, so it's different from null, so we push it to stack 2. So stack 2 push current left. Then we check, is the right different from null? The right of 1 is 3, so it's different from null, so we push it to stack 2. Then we go back to the condition of the loop. This time stack 1 is empty, so we exit this loop. We check, is stack 2 empty? Stack 2 is not empty. So we enter this condition. So stack 2 is not empty. So we enter this loop. We set current to the top of stack 2, which is 3. We pop stack 2. We print the current value, so 3. Then we check, is current right different from null? The right of 3 is 6, so it's different from null, so we push it to stack 1. Then we check, is the left different from null? The left of 3 is null, so we don't do anything. We go back to the condition, stack 2 is not empty. We set current to the top of stack 2, which is 2. We pop stack 2, and we print current, and we check, does it have a right? The right of 2 is 5, so we push it to stack 1. Then we check, does it have a left? The left of 2 is 4, so we push it to stack 1. We go back to the condition. This time stack 2 is empty, so we exit this while loop and we check, is stack 1 empty? Stack 1 is not empty. So we go back here and we check, stack 1 is not empty. We set current to the top of stack 1, which is 4. We pop stack 1. We print current. We check, does current have a left? The left of 4 is null. Check, does it have a right? The right of 4 is also null, so we don't do anything. We go back to the condition. We set current to the top of stack 1, so 5. We pop stack 1. We print current. And we check, current left different from null. The left of 5 is 7, so it's different from null, so we push it to stack 2. Then we check, is current right different from null? The right of 5 is 8, so it's different from null, so we push it to stack 2. And we go back to the condition, stack 1 is not empty, so we set current to the top of stack 1, 6. We pop stack 1. We print current. And we check, is current left different from null? The left of 6 is 9, so it's different from null, so we push it to stack 2. Then we check, is right different from null? The right of 6 is null, so we don't do anything. We go back to the condition. This time stack 1 is empty, so we exit this loop. We check, is stack 2 empty? Stack 2 is not empty, so we check, stack 2 is not empty. We set current to the top of stack 2, which is 9. We pop stack 2. We print current. We check, does current have a right? The right of 9 is null, so we don't do anything. We check, does it have a left? The left of 9 is also null, so we don't do anything. Go back to the condition. Stack 2 is not empty. We set current to the top of stack 2, which is 8. We pop stack 2. We print current. We check, does it have a right? The right of 8 is null. We check, does it have a left? The left of 8 is also null. So we go back to the condition. Stack 2 is not empty. We set current to the top of stack 2, so 7. We pop stack 2. We print current, 7. We check, does it have a right? No, it doesn't. Does it have a left? No, it doesn't. We go back to the condition. This time stack 2 is empty, so we exit this loop. Then we check, is stack 1 empty? Stack 1 is empty, so this means that there is no next level to process, so we break out of the loop. Once we break out of this outer loop, we exit the function, and we're done. So the final output is 1, 3, 2, 4, 5, 6, 9, 8, 7, which indeed is correct. Let's analyze the time complexity of this function. So initially we do some constant amount of work. Then what we do, we have these two while loops. If we look carefully at the body of these while loops, what we do inside every single iteration, we print current. A current is a node of the tree. So we print it here and we print it here. And we know that every single node of the tree will be printed exactly once. So these two loops combined overall will run n times. And the amount of work we do inside these two loops, which is pretty much the same work, is constant. So because we do a constant amount of work n times, the amount of work associated with these two loops is O of n. So overall, the time complexity will be O of n. What about the space complexity? It will depend on the sizes of these two stacks. So we know that at any point in time, either one of the two stacks contains all of the nodes of one level and the other stack is empty, or one of the two stacks contains the starting nodes of one level and the other stack contains the ending nodes of the level above or the level below. The worst case happens when one of the stacks contains all of the nodes in the last level of a binary tree that has all the levels filled, in which case that would be n half nodes. So we would have one stack with n half nodes, the other stack would be empty. So combined, that would be n half nodes in the two stacks. And so the space complexity is O of n. You can find the link to the code in the description below.